Okay, so good afternoon. I would like to take you in this talk through the activities of the LHCb computing project towards the LHC Run 3. And actually I found out I have a quite easy job to do today because I can reference a lot of talks from yesterday and even this morning, so you can look in other talks for more details if you're interested. Okay, so what is going to change in Run 3 for LHCb? So I thought the best way of doing this is that I explain to you how our data processing chain at the moment works in Run 2, and then we compare what's changing in Run 3. So this is a plot that you may have seen already. This is the online part of the data processing for LHCb. So out of the 40 megahertz bunch crossing rate, we have a hardware trigger which brings the rate down to 1 megahertz, and then we're feeding this into a software trigger. And in Run 2, we have split now this software trigger into two parts, which we call HLT1 and HLT2. And between the two parts, we're buffering the events, and we're doing full alignment and calibration of the detector in this stage, which is the best calibration alignment that we can do. And then we have the second part of the HLT, which does offline quality reconstruction for part of the data that is coming out of the HLT. So on the offline side, we have two main streams, let's say, that we are exporting on the grid for further processing. On the left side, this is what I would call the classical stream, where we do yet again the reconstruction of the events. And then there's a stage which we call the stripping, which is basically a further selection of the events and streaming into different streams for the analysis, which has a retention of around 40%. Now in Run 2, what we have introduced now is the so-called turbo stream. So this is, as we can do the offline quality reconstruction here in the trigger, so the data that comes out of this in this stream is already the best quality of the data that we can give to our analysis. So we do just a little bit of reformatting, which goes very quick on the grid, and the data is right away available for the analysis, and it works. So the best proof of this is that for Run 2 we have not done any reconstruction of any data that we have collected so far. If you look a bit here into I looked at these are the 2017 numbers, so you can look at the bandwidth and the kilohertz in the different streams. So you can see that with a much smaller bandwidth, we have a over proportional rate of events coming out for the turbo stream. So now what changes in Run 3? So this is the look at the 5 differences plot between this. Sorry, the 5 differences between these two slides. So basically there are two main differences. So one is that we are removing the hardware trigger, so we are triggering everything in software, and then the full stream is being removed. So we are aiming to export everything into this so-called turbo stream. So the turbo stream is also this is something that was explained yesterday by Rosen. The turbo data is much smaller than the raw data, because we have the possibility to only store the signal information, or if we want to, also the reconstruction information or anything in between. So if you're interested in this, please look at Rosen's talk from yesterday. So consequences for Run 3. So as you can imagine, removing the hardware trigger puts a huge strain on the software. So we have to improve a lot the software framework. Now the number of signal events goes up dramatically. Everything that we're exporting here in Turbo has 100% retention. So everything, because we know what we are selecting, these are all signal events, and they are smaller, and the luminosity goes up by a factor 5 in run 3 for LHCb. So as the signal scales with the simulation work will explode basically for LHCb. So then another thing that we have to look into is the user analysis. So this we need to have a way of for the users to do their analysis and their selections efficiently on the grid. Distributed computing infrastructure has to scale, and then of course we have to look into the computing model, how we're going to cope with all this data in run 3. So now let me go quickly through the different areas that we need to improve. So, the first one is just a quick slide on the timeline. So what we have done is 2 years ago, 1.5 years ago, we have kicked off this activity. Now by the beginning of the year, we have proven with the first demonstrators that what we envisage is technically feasible, and by the end of the year we have to provide the TDR for the computing, and next year we are working on another document for the LHCc to describe the computing model for run 3. Okay, so looking into the framework. So this is a plot that was shown 2 years ago in this kickoff workshop. So this shows basically, this is called Moore against Moore, Moore versus Moore. Moore is our trigger software. So it's the name of our trigger software, so it's against Moore's law. So basically what you can see here is the evolution of the hardware, and these are the trigger decisions that we are able to do in the trigger. As you can see, we are branching off here. So we need Gaudi, the framework that we're using in order to do the event processing. Was developed 15 years ago. Nobody talked about it at this time about multiple cores. So it was just this sequential event processing framework. So we are redesigning at the moment Gaudi. We are introducing task parallelism. We are looking into SIMD instructions, and to reduce cache misses that we are seeing with the current software. So where do we stand now currently with the framework? So the first changes have been implemented. We have ported around 100 algorithms into this new framework, and here you can see some scaling plots for the software. So you can see this works quite nicely. Now what I need to say is also that this is very recent news. So at the moment we are running into this was the lot of algorithms. Now if we are only running the HLT1 sequence, we are now going into we are observing lock contentions because we're doing too many mallocs of too many small objects in the software. So this is something. It's not nice, but on the other hand, it's nice because it's easy to fix. So as we go along, we are seeing more and more these problems. And now on the other side, on the plot below, you can see the memory consumption in this, and you can see that per additional thread we are adding something like 30 megabytes. Also, what we need to do is that now we have only concentrated on the algorithmic part at the moment, so we also need to introduce the filtering steps in this sequence. So more changes for the event model. This will become read-only. We have to make it, of course, composable. No inheritance, so pods in the data structures. Make it as simple as possible. For the vectorization, we're looking to SOA representations, and whenever possible, if we can go to single precision, this will help us, of course, also in the SIMD world. The vector description And conditions database need to be redesigned. They are very old software packages. For example, for the geometry, we're looking into a package which is called DD4HEP, and we're also looking into porting our software into different architectures. For example, ARM and Open Power. There's a talk by Nico on Thursday on this. This is a table I wanted to show you. This is from the rich photon reconstruction. So these are the speed-ups that they have done vectorization of this reconstruction part with VC, and basically they are seeing perfect speed-ups for SSE4 and AVX. For doubles, you see the factor 2, factor 4, and of course, if you go to float, you add another factor 2. Now, what we don't see, if you look carefully, if you go to AVX, you would expect another factor 2. We're not seeing this, so this is something we need to understand. Now we are also testing, of course, the evolution of the performance of the software. So every night with our nightly builds, we are running some timing tests. We are extracting some metrics from call grind, and then we can see some evolution of the performance of the software. So here you can see one of the algorithms where there was unnecessary mallocs removed. So this was some 20% improvement in the performance. Simulation. This is a plot that you may remember from this morning. So this is the pledge of WSEG as we forecast for the run 3 period, and this is the work that we need to do for the simulation as we are forecasting it. If we stay with full simulation or partly fast simulation, and you can see this is log scale, so we are an order of magnitude off. So what we're looking into is to go into faster simulation options. There are parts of it which are already in production, like this redecay, where the signal you're reusing the underlying event and just simulate the signal. And then there are other options which we're looking into. Just skip to go a bit faster. For simulation, other things that we need to do is the concurrency models between Géant and Gaudi are different, so we need to marry these two. There's a common work with FCC, which is called Gaussino. Gauss is our simulation framework. So Gaussino is the experiment agnostic part of the simulation framework, and this is currently developed together with FCC. So we need to reintegrate this, and of course we have to look into Géant V also for our Run 3 activities. So more areas for the distributed computing. So this is more evolutionary part. We need to look into the scaling of the distributed computing infrastructure. The analysis model I mentioned already. So we need to bring down the data into chunks that are manageable, and to look also into the I/O efficiency of the selection. So we will have very sparse reading of the data. So what we are thinking about is to group all these selections into bigger chunks, or to introduce multiple streaming layers in order to make them more manageable, and then also the computing model that we are looking at. Okay, so one last slide is something which I think is very important, is that the computing project itself is not doing all the work by itself. So we need the whole collaboration in order to migrate the software to this new infrastructure. So what we're doing also is we are investing a lot into training. So we have our own C++ course that we're giving to physicists. Also different languages, different tools, and so on. And then what we are doing is to trying to push the upgrade at the moment, so-called hackathons. Every other month, we have 1 week where we're concentrating on the upgrade activities, where we bring the software engineers and the subsystem people together. And there's a very nice space at CERN where we can do this. Okay, so this is my summary already. So as I've explained, there are major changes. The two major changes for LHCb in Run 3 is that we are triggering only in software, no hardware trigger anymore. We're exploiting fully the turbo concept, and this has repercussions on the software and computing. So we need to redesign Gaudi towards a multi-threaded task parallel framework. And the other big player is the simulation activities, simulation work that we're doing on the grid. The grid basically will be the grid will be only used for simulation work for LHCb. And towards the end of the year, we are working on a TDR. That's all I wanted to say. Thank you.
Common question.
I'm not sure I understand the full concept of the turbo flow correctly. Are you throwing away the raw data at the
Yes.
start?
Yes.
So can't do reprocessing?
No.
Right?
No. So if you look, okay, if you look at this is what we have done in Run 1. So this is you keep the raw data, you put it on tape, you can reprocess as much as you want. Here, the only thing that we're exporting out of the trigger is this turbo data, so the reconstructed data. So this is a one-shot. Yes. If we get it wrong, it's wrong. But as I said, it works. So we have no way. We did not have to reconstruct the full stream, for example, in Run 2.
But how do you deal with changes to, well, if you change the trigger software in this case?
We run the new version of the trigger. So the software what we are doing is that we are looking into the data as it comes out of the trigger. We will only use this version of the trigger.
So you are doing. Okay. So you are doing this tutorial for the new coding.
Sorry, say again.
The last subject is about the tutorial.
Yes.
To re-educate the software engineers. So I was wondering, you are changing the entire structure of the software every few years. That means we have to do this exercise every few years again and again.
We hope not.
Yeah, because
No.
this is a major change. So you want to keep this with even Run?
Yes. I mean, if you look, if you look at Gaudi, the framework that we're using right now, it was used in the last 15 years. So this is some period that we have to see. I mean, how things evolve, but it's certainly not. We're not going. Run 3 for LHCb is really a major change in the data processing. Now we hope that Run 4 is more an evolutionary part. Not for Atlas and CMS, I understand it's more the other way around. That Run 4 is the big step.
Thank you.
Right. Let's thank Stefan again.